Hello everyone. So we are going to start the part 2 from the topic deformation of solids. So let's start the discussion. The remaining part of the relationship between the shear stress and strain now we are going to discuss. So you see, let us consider a case. Suppose this is a solid piece, right? Here we are going to apply the force. The force will be acting in the opposite direction, at the opposite end of this solid, right? So due to this applied force, there will be some sort of extension. Let the extension to be described as x here, and the applied area of the solid substance, that is A. This F, it is the applied force. H, it is the height. This H, it is the height. And these are the angle of deformation. It is denoted with alpha. So let us consider these forces of equal magnitude, but they are in the opposite direction. That is, they will act parallelly to the surface A of the opposite ends of the object. Now this object is displaced by a small distance, that is your x, as I have already told you. So what will be the cases of shear stress and strain here? So you see, the shear stress here, it will be defined as a parallel, or you can say tangential force. The shear stress here, it is a parallel or tangential force which will be acting per unit area, which tends to shear the body. So shear stress here, it is equal to F parallel by A. So here F parallel, it is the force acting parallel to the area, and A, it is the area. Now here the shear strain, it is defined as a ratio of the displaced distance. So displaced distance was x to the height of the body. So height of the body, it is h. So shear strain here is equal to x by h, which is equal to tan alpha. Alpha, it is the angle of deformation. So x, it is the displaced distance, h, it is the height, and alpha, it is the angular distortion in the radian. Clear? Now let's discuss the relationship between the force and the elongation. So what is the relationship? Suppose we have applied a force, right? A force with a magnitude of F. A force has been applied, and definitely elongation will take place at the metal surface, right? Let's suppose the metal is a ductile metal. So you know the characteristic of the ductile metal, as we have already discussed in the previous slide. So this force, when it will act on the metal, right? So extension will happen. Let us plot the point. So here you can see in this plot we have different coordinates A, B, C, D and E. So what is A? This A coordinate, it is known as the proportional limit. B coordinate, it is the elastic limit. C coordinate, it is the yield point. D coordinate, it is the point of maximum force, that is the stress. And E coordinate, it is the fracture or breaking point. So if we plot the force against the extension, or extension against the force in the case of the ductile metal, we are going to get this type of graph. We are going to discuss regarding the graph, we are going to explain, but let us first see how it occurs. Again, if the stress against the strain in case of ductile material, the stress can be again plotted as stress versus strain. Here again the coordinates are same only, A, B, C, D and E. Now let's have some explanation. So explanation for the graph A, B and C here. See here, this is the ordinates, that is the original point O. This ordinates from O to A. This in this region O to A, you see the force or the stress O to A in this region O to A, for every graph O to A, right? In this region the stress, it is linearly. So when the stress, it is linearly increases, or it increases linearly with the extension until it reaches the point. So if we increase the stress, the extension will go on linearly. If we increase the stress over the metal from the coordinate 0 to A, in this region, upon application of the force, the extension will also increase linearly and it will reach the point A. This point A is known as the limit of proportionality. So what is limit of proportionality? See, the straight line, actually this OA, this is a straight line, right? This straight line OA, it obeys the Hooke's law. So what Hooke's law actually states that according to the Hooke's law, the restoring force Fs, restoring force means the force which will try to restore the metal to its original state, right? So the restoring force Fs, it is directly proportional to the extension. The restoring force, it is directly the force which will try to bring back this extension. It is directly proportional to the extension if the proportional limit is not exceeded. So suppose if we pull a material from this region to this region to A and we leave the material, this Fs, the Fs will be the restoring force. It will try to bring back the material to its original state until it reaches the point A. After A, it is quite impossible. So till A, if we apply the force, if we leave the material, then it will again come back to its original state. Clear? Now the next coordinate here, this force, actually this F force, it is denoted with minus Ke, where K, it is nothing but it is the Hooke's constant. Now why negative sign is given here? This negative sign actually here, it indicates that the restoring force, it is in the opposite direction to the direction of the increasing extension. Yeah, isn't it? This restoring force, it will try to bring back the material to its original states. Thus here the sign, it is negative. Means earlier we have applied the force. This force, it is trying to extend the material, and by virtue of this force, extension of the material, it is taking place from the point O to A. But once we leave the substance at a point A, after reaching the point A, the force, restoring force, will act upon this restoring force, will try to bring it back. So it is in the opposite direction. That's why we are using a negative sign here. The point B, here the point B, it is nothing but it is the elastic limit of the material, right? So what do you mean by the elastic limit? See, beyond this point B, if we go far beyond this point B, the material is permanently stretched. Means after crossing the point B, the material will be permanently stretched. It will not come back, right? And it will never regain its original shape and line. If the force stress is removed, the material has a permanent extension OT. Suppose here, after crossing the point B, if we leave the material, if we leave the force at the point C, then it will come back. It may come back, but it will have a different extension. Here it will come as OT. Means if it comes back, then you will have one extension. This is OT. It is nothing but it is a hysteresis actually, right? Again, you see the area between the two parallel lines AO and CT. AO and CT, this area, this dotted line. Here see, you see AO or OA and CT, right? It represents the work done. This area actually, this dotted line, red dotted line, and this line, this area actually, it shows the work done to produce the permanent extension OT. This is the permanent extension OT. OT will be the permanent extension of the material. So this area, it is showing the work done by the force. OB, what do you mean by OB? OB, it is nothing but it is a region of elastic deformation. And point C, it is the yield point. So the yield point marked as a change in the internal structure of the material. If the material has reached the point C, upon application of the force, it, after reaching the point C, it have a internal structural change in the material. The plane actually, the layer of the atom of the material, they slide across each other, resulting in a sudden increase in the extension, and the material thins uniformly. If we pull a iron thread or iron rod like this, immediately after reaching the point C, the atoms of the material or the metal, it will slide over each other, resulting in a sudden increase in the extension. You see, there is a sudden increase in the extension, sudden increase in the extension, right? There is a sudden increase in the extension, resulting in a sudden increase in the extension, and the material, it thins uniformly. Now, what do you mean by the region CDE? So the CDE region, it shows the plastic deformation. Plastic deformation means from here the material will never come back to its original coordinate. CDE, C, D, and E. C, D, and E. C, D, and E means the material will not come back to its original point. So when the force, or you can say stress, increases, the extension strength, it increases rapidly in this region. The point D, what do you mean by the point D here? The point D, it is the force on the material is maximum. Here the force on the material at the point D, the force on the material is maximum. So it is also known as the breaking force. If it reaches the point D, it is the breaking force. And sometimes it is also known as the ultimate point D, it is also known as ultimate tensile strength. It is the ultimate tensile strength, right? And point E, it is the point where the material will break or it will fracture. So till D, the material will not break, but after D, the material will get fractured or it will get broken. Clear? So for ductile material and brittle material, this is the stress strain relationship graph. See, the ductile material, what will happen with the ductile material? The ductile material, they undergo plastic deformation before breaking. What do you mean by plastic deformation? Plastic deformation means it will not come back to its original point. Example, steel, copper, aluminum. Steel, copper, aluminum, they are showing the plastic deformation. The graph, they are showing the plastic deformation. For brittle material, it don't show plastic deformation, such as example is glass. It will directly break. Clear? Now the strain and the stress relationship, that is the stress strain relationship for polymeric material. Let us take example of rubber, and this is the graph. So let us discuss this graph. So what do you mean by this graph? You see, we all know that the rubber, they undergo generally the elastic deformation, means always after removing the applied force, the rubber always try to come back to its original state, right? So it able to regain its original shape and length when the stress is removed. And thus the rubber, they never follow the Hooke's law, right? But here there is a scenario you need to know. You see, the strain produced when the decreasing, this is the strain. So after releasing here, after releasing the force, it will regain back to its original position, right? So releasing, or you can say the decreasing stress, it is denoted by XY curve. So the strain produced when the decreasing the stress, that is XY, it is always greater as compared to the strain produced during the increasing stress, that is the WX. This is the increasing stress curve. The upper one, this is the increasing stress curve. The lower one, this is the decreasing stress curve. So simple, the strain produced when the decreasing curve, or you can say decreasing stress curve, it is always, the strain, it is always greater as compared to that of the increasing stress curve. The decreasing stress curve have a greater strain, right? So this shaded area is nothing but it is known as what? The hysteresis loop. And actually this hysteresis loop is nothing but it actually represents this dotted line, or this is shaded area. It actually represents the energy loss per unit volume. This energy loss per unit volume, it is represented by this dotted line. So the energy loss, it is lost in the form of heat dissipation, means heat will be released. Clear? Now let's see for another type of material, the relationship of stress strain for polyethylene. We know that what is polyethylene, right? The polyethylene, we all used to call it as a plastic. So the polyethylene, they have a plastic deformation. So this is the increasing stress curve, this is the decreasing stress curve. The polyethylene, they generally undergo plastic deformation and they produce a permanent strain. Yes, right. If we stretch a polythene, it never comes back to its original position, and thus they don't obey the Hooke's law. So I hope you have enjoyed the class. If you like my video, just press the like icon. You can share this video and you can subscribe to my channel. Thank you once again.